I wonder, how do you perform your square roots in the mathematics department? Although I did it and it looked cumbersome, but today I have been acquainted with a approximation formula which very fast converges into the right root of a given rational number. So how do you perform it? Before it, let us go to the theory and just generalize it. What I will say is that root over a number, positive number a, and I will make an approximation to it, and this I say ad hoc that it will be very close to half times here in whole brackets an approximation to root a. This will be a crude approximation. B is a crude approximation. Here the current has gone and we are destined to perform it in the darkness. Okay, the half times within brackets the crude approximation plus the number whose square root is needed divided by that crude approximation. This will give us a very good approximation, a nearer approximation than the crude approximation to root a. First we'll prove that. So how do you do that? Let the crude approximation be b, and it is equal to, for example, root a plus something of a small quantity del. We write it. Okay. We then perform the calculation on the right hand side of the first equation 1. We perform the approximation and it comes out to be half times b. We substitute b from equation number 2, and b is written as root a plus del. Okay, very good. Plus a by b that you see in the right hand side of equation 1. A by b we have substituted as root a plus del, isn't it? Okay, now we go on. We write it as half times. See, we can take as an LCM this number in the beneath, root a plus del. If we take this root a plus del, then this will come out to be root a plus del times root a plus del, then root a plus del whole square plus a, isn't it? And root a plus del whole square gives you a plus 2 del times root a plus del square, isn't it? Plus this a plus a. Okay, we can close this in brackets. Now this del square term is very small. If our crude approximation is a little bit nearer to the real value, then we can neglect this plus del square. Then we neglect it. Okay, we neglect this del square. Then what we have is just mere calculation, half times root a plus del we are going in rough lines. We should go in parallel lines. Yes. And what we see over here, a plus 2 del times root a plus a. So a plus a gives you 2a plus 2 del times root a. Then 2a plus 2 del times root a. As we see here, there is a half, and here 2, and here 2. We remove this 2 and the half and simplify our results. For visualization, it will be better to remove the smudges. Okay, here a plus del. See, root a plus del, and here a plus del root a. If you take root a common from the numerator, then you will get root a plus del over here, and root a plus del also over here. Provided these things are not 0 and these things are not really practically 0, we can cut them, and this gives us 1. So the result gives us equals to root a. But here we have cheated somewhere. We have cheated here, saying that the del square which we have missed over here, the del square very close to 0. We have taken del square very close to 0. If this condition is maintained, then we can write that the right hand side of what we have taken ad hoc gives us the value root a. See, we wanted the value of root a, and we find it through an approximation. Means by crude approximation we reach the right root a. We can reach it faster if this del square, that means del is nearer to 0. The more nearer is it to 0, the much faster will the thing converge to the value root a. So we are ready to do a sum which will illustrate our results. Okay. So first of all, we write the formula, that the approximation formula, which goes like that. That root over a equals half times crude approximation plus a by crude approximation. Okay, now this is pretty clear from here. So what it does is approximate result. Okay, so we'll see its magic, how it operates and how it converges really fast, swift. For example, take a number, say 9. we want to find its square root. Now we don't know its square root, and that we don't know that 3 times 3 equals 9. We guess something. Let 2 times 2 equals 9. Then 2 is the crude approximation, and b equals 2. Okay, then root over 9, the formula says, is very close to half times b is 2 plus a is 9 by 2. Okay, then these things give us half into 2 plus 4.5, isn't it? The 2 plus 4.5 is 6.5, and 6.5 divided by 2 gives 3.25. See, we have come close to 3. Now we can further extrapolate our approximation methods, for we have got a better approximation than 2. It is 3.25. Now we'll replace b by 3.25 and find root 9. And now root 9 is very close to half times. See how fast the result converges will be demonstrated now. 3.25 plus a by b. A gives you 9 by 3.25. If you perform this sum, you will get very close to 3.005. See how close we are getting. And if you put this 3.005 in the algorithm, then we will get another number which will be much closer. So in this way we can perform square roots of any number. So we will take now the square root of another number and see the results. Let the number be the square root of let it be 36. Okay, or shall we take a larger number? Or we can take 144. Square root of 144. I will do it to the first approximation and the rest will be your job. We know that 12 square is 144, but say we don't have that intuition to find the square root of 144, and we imagine it to be close to 10, because 10 square is 100. Then we'll by first approximation get half times 10 plus 144 by 10. This will give me half times 10 plus 14.4. 10 plus 14.4. What is 10 plus 14.4? Is 24.4. Okay, 24.4. The results are obscure here. 24.4. This is due to the limitation of my chalk. The uncertainty in its position is magnifying. 24.4. Then half times 24.4 gives you 12.2. See, you get a very close result just by considering a very crude approximation 10. And when you go further and calculate by taking the approximation 12.2, you will get much closer, and this will converge very rapidly. So this is something which I have learned and have shared with you. I think you have got the algorithm, and I suggest you to practice it in your daily life. That's all.